In this section, we're going to talk about exponential growth and decay. And this is basically the first section you're going to see in a differential equations class. But since we just give you the solution, we go ahead and just run with it for now. So you don't actually need to solve any differential equations. We'll just give it to you. But here's what a differential equation. A differential equation involves an unknown function and its derivative, right? And so here, this time I have t. This is a t. I should have switched this to an x. Sorry. Um, so here we have an unknown function and its derivative. So dy dx is some function of x and y. And in this case, we're going to be using this. This is what we're going to use the entire chapter. Is the rate of change, right? Its derivative is proportional, some proportional to how much is left. And there's a couple common things they use. One of them is population, which we'll do one of these. One of them is like carbon dating and molecule decay. So that's another one we'll talk about. And then I forget what the third one we talk about is. Oh, Newton's law of cooling. We do a cooling one. And so this just appears in a lot of your science classes. So we're going to leave math world for a second and go to the science world for a bit. So the only solution to this equation is this, right? So that is the only solution. And in a differential equation class, you go through a lot of stuff to prove that is the only solution, it is what it is, and it's unique, it exists, and it solves the equation. We don't need to worry about it. What we're going to do is just take whatever the initial condition is, right? Whatever our initial condition is here is equal e to the t. So we're just going to use this equation. So basically, it's just, can I solve stuff using this equation? Um, so what we're going to do here, hold on, let me open up. Let me open up. So, oh, good news. I did email and get the proper textbook. I do have the right book in front of me now. So let's start with this. So we're going to use the fact that the world population was 2,560 million in 1950. And then I don't know why they just didn't write this in billions, right? 3,040 million, which sounds weird to say because no one says it that way, right? Is the population for this to model the population. So we're going to use these two facts to model. Assume the growth rate is proportional to population side. What is the relative growth rate? So we're going to try to find out what this k is, right? Use this model to estimate the population, the world population in this, and then use it to predict the population of this. So let's break this down. So what do we have here? So we're going to say the following. So we're going to we need to just go ahead and establish what time zero is. So we're going to say time is equal to zero when it's 1950. And this is actually not too, this is pretty standard when you're working with populations. You're going to say, I knew the population, the first time you know the population, that is time equal to zero, quote unquote, right? So here we're just going to use that as time equal to zero is 1950. So that means y of zero. So my initial value is 2,560. And so here we can write y of t is equal to 2,560 e to the k, and I don't know what t is, but here we're going to plug in. Oops. Let's go ahead and leave that as t. So y of t is this. And so here we have one equation with basically, so here we can establish our base. So we're establishing this base equation. We're going to use the second one to find out what k is. Let me show you what I'm going to do. So when y of t equals to, so when t equals, see if I can do this and not get you super confused. When t equals 10, it's going to be 1960 because that's 10 years later, right? I'm going to put t in, and we're going to say t is in years, right? Just so we have baseline for it. So t will be in years. So from t is 10, it's 1960. So I know what that is, right? So I'm going to say y, oops, forward, erase. All right, so y of 10 is equal to 340, which is equal to 25560 e to the k, which I do not know, times 10. All right, so here's an equation. What type of equation is this? Does anyone know? Did you just solve a whole bunch of those? Anyone going to write in chat? It's Monday. No one's going to talk to me today. That's okay. Yeah, we're going to use log to solve it. Yeah, so we're going to use log to solve this. So let's go ahead and solve this. So here, if I was going to solve this, I'm just going to take the log of both sides. So here I'm going to just take ln. And so here we're going to take ln of 340. Equals ln of 260 e to the k, or 10k, right? Let's look at 10k. But notice here, if I multiply into things, that I can rewrite this as ln of 256. Plus, make sure I'm doing this correctly. Yeah, 256 plus ln of e to the 10k. Well, e to the 10k, this is just 10k, right? And so here I can minus these two. So I'll have ln of 340 minus ln of 256 equals 10k. Anyone get lost up to this point? Make sure I haven't lost you yet. Anyone lost here? So what I did is I took the log of both sides, and since this is e, technically, I guess I did this the hard way. I think I actually legit did this the hard way. Let me do one more step. And then I can show you how I could have probably should have just skipped to something. I didn't leave myself enough room at all. I'm writing way too big. Because this just becomes ln of 340 divided by 256, or 2,560. Equals 10k. So k equals 1 over 10 times the log of 340. Now what did I do that I probably should have done first? Well, I should have divided out the 256. That way I didn't have to use this log rule or this log rule, right? I could have just skipped straight to here. Everyone see how I could have just done that? Anyways, if we plug that in, you're going to get k is roughly equal to 0.017185. Okay, so we get our k here. All right, so once we do that, we get our official population equation. So y of t, or you can use p. I think your book uses p when it solves it. So y of t equals 256 times e to the 0.07185. I forgot one. T. All right, so the other two questions, like, oh, so what's the relative growth rate? This is a relative growth rate. It's just what k is, right? And use this model to estimate the population of 1993. So 1993 would be t equal to 43. And that means y of t, we'll just plug that in into a calculator in a second. And here at 2020, that'll be t is, oops. Let me just make this easier. So 1993, since I don't have room, sorry to erase, will be y of 43. And then 2020, which would be y of 70. So are we going to do this by hand? Heck no, right? You're going to use a calculator. So All right, so let's just open up Wolfram Alpha. All right. E to the 0.017185, and then here we're going to type in so 43 for the first one. Oops, I don't have that done correctly. There we go. Make sure it's done correctly. All right, so here I get about 5.35. I'm just going to write it as 5. I'm going to say this is 5.35 billion. And then here we're going to be at and here we'll just swap this out with 70. And we're at 8.52. This would be 8.52 billion. Okay. Notice here I've written this in terms of million. Technically, if I wanted to, I could write it this way. I just don't want to have all the zeros in my calculation. So please make sure your units match. And so this is just kind of how you use this. And so the whole point of this chapter is kind of to mess with this. And does it make sense that population grows as proportional to how many people are around? Like the change in population is proportional to how many people? Yeah, sure, right? More people, the more growth there is. It's kind of like this is a simplified model where we don't have, where there's not a resource cap. You can make this model much, much more complicated, right? And while it may take humans a long time to populate, if you leave, if you have a moldy piece of bread and the mold grows quite quickly, right? It's exponential growth because there's a lot of bread until it gets super moldy. So, all right, let me leave this up for 1 second and take a drink and then go to the next page. All right. You know what? I am super curious real quick. What is the world pop right now? I think we're actually Wolfram Alpha. World population. There we go. It's not bad, right? Here's an actual chart of the world population. Notice here, and boom, exponential growth, right? It's just what it is. But it's actually a teeny bit. This is yeah. All right, so let's go to the next page. All right, so now we're going to talk about radioactive decay. So assume the half-life of radium 226 is 1,590 years, or 1,590 years. Say that correctly. Technically, you're supposed to write. I just leaving it as RA. Technically, you write 226 over 88 if you're a good chemist. I'm just not a good chemist. That way you clearly define which molecule you're talking about. All right, so sample, so the half-life of radium is this many years. So find a sample of radium is this. Find the formula of the mass of radium was after 2 years. So here, given an initial sample size, how much after this year? Find the mass after 100 years or 1,000 years. When will the mass reduce to 30 milligrams? So we're going to solve each one of this. So let's start first by writing out our formula. So here we're going to say our mass of how much we have left of is a function of time is equal to the initial amount. So I'm just going to write m0 e to the kt. So here I'm just writing the formula before. I know what the half-life is. The half-life of radium is when it's this many years. And so another way of saying that is I have half of my initial amount when it's been 1,590 years. And so this lets us solve for k. So here, if I divide, this time I will divide. If I divide this by this, I just get 1/2 equals e to the k 1590. So if I take the log of both sides, so here if I log of a half is equal to k 1590. Oh, it's like, where's my mouse? I lost my mouse. All right. Well, log of a half is the same as minus ln of 2. Okay, of 1590. So this, I'm just using log rules to change this. And the reason I'm changing this is because then when I solve for k, it's equal to minus ln of 2 of 9. Your book doesn't give you this thing, but here if I have a half-life, that's equal to ln of f2 divided by k, or k is equal to ln of 2 divided by the half-life, where h is the half-life, and a half-life is how long it takes to go. So your book doesn't give you these formulas. I'm going to just give them to you real quick. So this is always true. And then the sign here, since this is decreasing, so for half-life, it'll be decreasing. If it's how long it takes for a population to double, you can use the same thing. And these are very common in population models and in half-life models. These are super common. So, is that a negative ln? Yeah, so this is negative, this is negative, this is negative, and this is negative, since we're dealing with half-life. If we're dealing with growth doubling, it's the other way. Yeah. So here, I know what my half-life is, 159, or 1,590, sorry. And so k is just equal to ln 2 over that. And this is always true, right? It doesn't matter where h is your half-life. So in this case, we're going to get k equal. What do we get k equal to? Here we get k equal to, your crazy book just leaves it that way. Why, crazy book? Why? Why are you so crazy, book? We're not doing that way. Nope, we're going to calculate this. We're going to calculate it. So let's just crunch that number. So let's just crunch that number. So I have minus ln of 2 divided by 1590. It's a really small number for sure, right? So here I get a decimal approximation is negative 0.0043941. So here we can just, oops, it's kind of hard to copy it if I get rid of it. Your book does it a different way. If you want to do it the book's way, that's fine. Because your book just leaves it as this mess and then writes the formula. But I'm going to give you the option of doing it both ways. So let me show you what both ways are. Let me actually give you the option. That's good enough. Do about 4 decimal places or 4 significant figures, right? Not 4 decimal, but 4 significant figures. And you know what I mean by significant figures? Significant figures means if you put it in scientific notation, you would have four digits. Okay, that's what it means. Significant figures. All right, so the MT formula, hold on, let me make that look less like garbage. So the MT formula, so the mass is equal to my initial mass, depending on whatever it is. Oh, in this case, I know what it is. It's 100 milligrams. So 100 milligrams times E. I can put this in. I can put minus ln of 2 T over 150 at 90. That's fine. Or you can put in this. And in this case, I'm not positive one's better than the other. Or you can put in this to the C. So here we solved the first one. So this is the answer to A. We had to figure out what K is. And then we can plug it in. What's the mass after, find the mass after 1,000 years. So here for B, we're just going to put in M of 1,000. And so we're just going to crunch through that number. So it's 100 times e to the minus ln of 2 times 0, 0, 0. You can leave this as ln to a half. That's fine. They're the same numbers. 1590. Okay, let's type that in. Let's type that in. Get ourselves an answer. Hello, hello. Where'd you go? Oh, there you are. All right, so let's just say we'll have 100 e raised to the fifth, and we're going to do this for 1,000 years. All right, so here we get 64.2 or 64.66 or 0.67. That'll be fine. Whatever, do whatever the book asks you to do. 64.67. It'll tell you how many significant figures in the book. All right, so the last one is we want to say how long until it's 30 milligrams. So here we just do this. E to the minus ln of 2p over 159. Here we divide this out. So I'll get 3/10 equals e to the ln of 2 t over. And so I get the log, since I'm kind of running low on room, log of 3. So we take the log of both sides. So divide this out, take the log of both sides. We get ln of 3/10 is equal to minus ln of 2 t over 15. That look more like a 0, not like a 6. Okay. And then here we're just going to, that means t is equal to the ln of 3/10 times 159.50 divided by minus ln of 2. And then we'll just crunch that through in a calculator. Or another way of doing this in a calculator, we just have it solve it for you. This is another perfectly fine way of doing it. So yeah, that should give you the same. Yeah, so this is what we have, right? This is legitimately what we have. They flipped these two. So they flipped this upside down to make this positive and make this positive and took out the negative. So we just hit approximate, and that's approximately 2,761 years. Okay. Or 62 years, I guess, if we're going to round correctly. So t equals 2,762 years. Okay. All right. And so this is kind of how you run and play with these formulas and how you do the math for this. If you're going to use this equation, you're going to set up, if it's growth, it's a positive k. If it's decay, it's a negative k. And you're just going to mess with this same equation, do the same sort of things throughout this chapter. All right, so let's do the last one real quick. Let's do Newton's law of cooling. And then we'll go to the next section. All right, so here's Newton's law of cooling. So the change in temperature is equal to some proportionality constant that depends on a lot of things. It's like the thermoconductive properties of your environment versus the thermoconductive properties of the object you're cooling. That's a lot of things. And then we're going to take our temperature minus the ambient temperature, right? And so notice here that if this is hotter than the ambient temperature, this will be, hold on, make sure I have that correct. Temperature. Hold on, is my K? I think I learned this backwards. And the reason I say that is, yeah, taking the logarithms. Yeah, because in this case, you're going to have negative Ks. You're going to have negative Ks. So I think I've learned it backwards. And the reason I've learned it backwards is because when I learned this, it was the surrounding minus the object. That way, if the object was hotter, you'd have a negative K, and you would notice that the temperature would leave. And then here, but here we're going to get a negative K when you solve for these ones, which is fine. And that means the object's going to go in the other direction. It's fine. It's fine. It doesn't matter. So this is the temperature. It doesn't matter. Mathematically, it works out the same. Just physically, it makes a lot more sense one way. And your book does it opposite the way I was taught as a physicist. So let's just go through this real quick. So this is the surrounding temperature, and this is the temperature of the object being cooled, quote unquote. Okay, so we're just going to do an example. Say I have a bottle of soda pop at 72 degrees placed in the fridge. Right? So I take room temperature soda pop and put it into a normal fridge, right? Normal fridge should be something above freezing, but around less than 50, right? After half an hour, the soda pop is cooled to 61 degrees. What is the temperature of the soda pop after another half hour? How long does it take for the soda pop to cool to 50 degrees, right? And so this is just a common question. So let's crunch through it. All right. So see how your books wants to define this. So here we're going to do I see what your book's doing. I see what it's doing. So let me see if I can explain it to you. So here we're going to have dt of dt is equal to some k of t minus ts, right? And they're going to say, all right, well, the surrounding temperature in this case is 44 degrees. And so here they're going to write this is equal to k t minus ts, or 44. And here the initial, hold on, let me put in the initial temperature too. The initial was 72. So this is what we're solving. They're going to do a quick change of variables. They're going to change this to dy dt, where y equals dy. And they're going to say y here is equal to t minus 44. So this is what y equals. And then when y naught, our y naught is going to be, so we're just changing variables. We're going to just say, instead of for solving the temperature, we're going to solve for y. Y is going to be t minus 44. And then the initial thing of 72 says 72 minus 44 is equal to 28. So it's just doing a quick change of variable to get it into the form that we know. So here, then we can write out the very simple equation we've had working with all along. This is y naught e to the kt. And I know what y naught is. Y naught in this case is 28. So in this case, it's going to be 28 e to the kt. And then we can just solve this normally. But when we want to find out what our temperature is, we got to go back to this. We have to go back to this right here. All right.
What does that say behind the y? Between the y and the e?
Why not?
Why what?
Y of 0.
Oh, okay.
Yeah, sorry, y of 0. I'll erase that. All right. And so in order to do Newton's law of cooling, though you don't have to do anything fancy, your book's always just going to translate it. And that's what your book's doing. And it's not a bad idea. It's not a bad idea at all. That way you can just keep using the same methods. All right, so we want to find, after an hour and a half, or half an hour, sorry, the soda pot cooled to this amount. What is this amount in our translated variable? So y in this case would be 61 minus 44. And so 61 minus 44 is 17. Yes. 17. And so here we have 17 is equal to 28 e, and here we're going to have t. T here is in hours. Okay. For here we have t in hours because that's just what we're using. Or no, let's just do it. Let's not do it with fractions. We're going to put t in minutes, so we don't have to do it with fractions. Okay. T will be in minutes, not equals minutes. But, you can do it in hours. It works out the same. I'm going to do it in minutes just so we don't have to do fractions. So this will be 30. Okay. We divide out the 2, same thing we did before. So 17 divided by 28 equals e to the 30k. So we just solve it out. And then from there, we'll have ln of 17. Oops, that does not look like 17. Apparently, I should have left more room when I wrote these notes. 30k. So k equals ln of 17 divided by 28 all over 30. And that is roughly equal to minus 0.0163. Oh, no, there's another 6 in there. All right, so here we have this. So what is the temperature of the soda pop after another half hour? And so here we're just going to solve the other two things. G, I don't need that much space. I guess I'll just zoom on in. Now I have room to do what I want. I'll just do this. There we go. All right. So now we know what K is. So another half hour would just be what is y of t equal to when I have, this starts at 28. So 28 e to the minus 0.01663. Sorry, this is getting a little too small. Let me just open a new page just to answer these two. Sorry about this. I just don't want to write too small, but I don't want to just crunch it all in at the same time. New page me real quick, so I have room to finish these two problems. Hi. 5 new. Yeah, just give me a little 5 by 5. That'll be plenty. Whoop, there we go. This will be plenty of room to finish what I need to do. All right, so here, hopefully. Sorry about this. If your notes are incomplete for this little part, I will not grumble. Just because I didn't leave you the room for it. So 28 e to the 0. Minus 0.01663. This is a teeny bit smaller. Okay. T. And I want to, but here I wanted to solve for when it was another half hour. And so that'll be at 60. And I just crunch this through a calculator. You can crunch that through a calculator, and you're going to get roughly 14.3. And remember that y, and so t is equal to y plus 44, right? So because y was equal to, back to that real quick, y is equal to t minus 44, so t equals y plus 44. And so y plus 44, so that means this is approximately equal to 54 point, or hold on, I did this wrong. This is only 11, or this is only 10.3. This is 50. Okay. So and all you have to do is just plug in for that, and then the other one is just going to be solving. I want to know when it's 50 degrees Fahrenheit. And so 50 minus 44 will be 50 minus 44 will be 6 is what I'm going to be using for my y. So y equals to 28 e to the minus 0.01336 t. You're going to solve for t. And that'd be the same thing we did before. So 6 over 28, take the natural log. Gives me minus 0.001663 t. And then if you solve for that, you're going to get t is roughly equal to 9.26 minutes. Okay. So the other thing that's kind of funny about Newton's law of cooling is you're always shifting your number one way or another to make sure the math works out right, based off of whatever your ambient temperature is. It's a little bit cumbersome, but doing it that way makes it easier because this equation is simpler. This equation becomes simpler to work with. Okay. All right. Any questions on any of this? And then we're going to talk about interest real quick. I'll leave this up for 1 second for you to copy. Okay, so let's do the last thing notes. The last thing we want to talk about is compound interest and continuously compound interest. And so you've probably seen these, probably worked with these formulas before, but if not, we'll go through it. It's just where your book wants to put it. All right, let's make me just a little bit better. There we go. So here, the amount after t years for interest rate is based off the principal equals 1 over r over n. This is the rate per year times the number of times interest is compounded. According and notice that your rate, usually they'll say 7%. Remember, for that 7%, the rate is 0.07. Just be very careful about that. And so this is the formula you use. It's an exponential formula, of course, right? Because here I plug in t, I have something. This is, you evaluate it to be something, and raise it to the t power. If we take the limit of this, remember the limit of this is e to the rt, so that's what it was defined by. So here we'll go ahead and put that in here. And so we'll do something that may matter to you guys, right? Let's talk about student loans. And this isn't too far off from what it is. I think the average student lives, it's somewhere around this number, right? And I think student loans currently are at 0% because of the pandemic relief bill, but they're often around like 6 or something. It's pretty bad, right? So, and this is about average what it takes for you guys to go to college. It's expensive, I know. I still have student loans I'm paying off from it all. Trust me, I know. So let's just do this. So we're going to take out a student loan. We're going to find out after 4 years, like, so you take out your loan for 4 years, and we're going to figure out annually, semi-annually, monthly, daily, and continuously. So we're going to do this one a bunch of times. Okay. So given compound interest common rates, we're going to do this. And so here, our amount after 2 years. So let's just write down our formula. So if the first one is 3,000, 333,000 times 1, oops, times 1 plus, so 7% would be 0.7 all over n. This is how many times we're compounding it per year, times n times RT. All right, so we want to find out, and so let's just do annually. So annually, so that'd be t equals to 1, or no, here we're doing it for 4 years, so annually for 4, and then n in this case, so n is equal to 1. That's how many times we're compounding it per year, so once. So it'll be 30,000. Oops, 0.07 all over 1 times 4. And this is a roughly equal to 39.32. 3.88. We're going to do the same thing again. The only thing we're going to change here for the semi-annual. My computer's getting a little crunchy. I'll have to kick stuff off before we do the next set. Here, if we do this for that, we'll have, this will be the exact same, so it'll be 30,000. The only thing we're changing here is 0.07. This will be 2, and this will be 2 times 4. And if you crunch that roughly through, you get 39,504.27. So notice as we do this, the amount goes up, right? The more you compound it, even though it's the same interest rate per year, the more you compound it, the more times it, the more it becomes. I'm just going to give you these last two numbers. You get how to type it in. The last two numbers here are going to be 39.9661. There's 0.96. I cannot write. It is 39,661.62, and then for daily is equal to n would be 365 days. We'll have a and notice how the more we compound it, the more this number seems to collapse to a certain number. And so we can compound it continuously. I don't think any, I keep looking this up. I don't think currently any loan you take out will be compounded continuously. I think most of them either do it monthly or sometimes, I think monthly is kind of the standard. So anyways, and so let's just do what the continuous is. But technically, I bet continuous will eventually become the new standard just because you can always see your money live. So we'll have our principal of 300,000. It'll be e to the 0.07t, or in this case 4. And I do not have that number in front of me, but we can calculate it super fast. So let's just calculate that number. So it's going to be 30,000 e to the 0.07. All right, times 4. And we get this. All right. So 39. Let me just put this over here and I'll write it for you guys. So 39 comma 6. 39, 693, and 89 cents. Okay.